This week what we're going to do is we'll do the next chapter and then we'll spend our next class entirely on catch-up.
So tomorrow?
Yeah, and then we'll push the last chapter to next week and then spend another day next week getting completely caught up. So halfway after the next 2 weeks, you guys are completely caught up on all the material.
Are we giving a test next week?
And then I'll give you your test at the end of next week. You'll turn that in at the start of the following week, and we'll be done.
Cool.
Okay. So today we're talking about the first law of thermodynamics. The first law of thermodynamics. Well, yeah. Should I just throw up the law there first, and then we'll cover the material, how to put this? The first law of thermodynamics, in a nutshell, it says energy is conserved. It's our energy conservation law when we're dealing with thermodynamic systems.
Okay.
And most of what we'll be dealing with throughout this chapter will be ideal gases. And so it's a statement that says energy is conserved in thermodynamic systems. And here's the way that the equation is awfully written is U2 minus U1, which is the same thing as delta U, is equal to delta Q minus delta W. So let's read that statement really quick. U, now you're used to thinking about U as a potential energy when we're talking about gravitational forces.
Yes.
That is not what U is in this context. So for the next 2 chapters, put that notion of U out of your head. U just stands for the internal energy of some system. U is a system's internal energy. So you can think about it as adding up all the kinetic and potential energy inside some system. That's U.
So both kinetic and potential?
If there's potential energy in there. For the systems we'll be talking about, so we'll mostly be talking about monotonic and diatomic ideal gases.
What do those mean?
Monatomic means just helium gas. Diatomic is like oxygen gas, because oxygen is 2 oxygen atoms together, whereas helium's a single atom.
Oh, I see.
Monatomic means the molecule is composed of 1 atom. Di meaning it's composed of 2 atoms.
Okay.
So we'll be talking about gases like that for the most part today. And with gases like that, almost all their internal energy is just kinetic energy. You might remember from our last chapter, one of the things we spent a lot of time talking about was what did we call it? The molar specific heat. And we calculated the molar specific heat for a bunch of different types of gases and solids.
That's right.
You remember that?
Mm-hmm.
And we were basically keeping track of where the energy would go if you heated up a system. Right? And so some of the systems, we thought about them as like atoms vibrating on a spring. And so if you're vibrating on a spring, as a spring compresses, that stores up some potential energy. And as it contracts, that releases that potential energy and converts it into kinetic energy. So you can see how vibrating atoms on like a solid would have some potential energy. When we're talking about monatomic and diatomic gases, there's almost none of that. So all the energy is just in the fact that they're moving. So it's almost purely kinetic energy.
Yeah.
So U in general means the internal energy of the system. For our specific cases, for most of the problems we'll be dealing with today, U will just be the kinetic energy of our system. Because basically all of its internal energy will be kinetic energy.
So how do you calculate U? Just the same as just K?
So here will be, we'll get to an actual brute calculation of U, how much energy is in a system.
Okay.
But first let's understand what this is saying, and then we'll go back and cover this in the order the book gives it. So in short, what this is saying is the change of our internal energy of a system. So I have some gas, and I'm going to change the internal energy of that gas. First off, we know how to add energy to the system. How do we do that?
Work?
You heat it up. That's what we've been doing this whole time. For the past 2
up.
chapters, we've been heating stuff up. You take an ice cube, you heat it up.
Okay.
Right?
So you just change the temperature and pressure, right?
Not necessarily changing the temperature. Well, it will change the temperature. Temperature is a measure of the internal energy of a system. So for the gases we're talking about, U here is going to be some sort of function in terms of temperature. You can express the internal energy as a function of temperature. The more internal energy it has, the higher the temperature. The less internal energy, the less temperature.
Okay.
But how do we increase the energy of a system? How do I get those atoms vibrating faster, give them more kinetic energy? I add heat.
Yeah, that makes sense.
Okay, so if you add heat to a system, then the energy in the system has to go up. Now what about if a system does work? If a system does work, it loses energy. If you do work, you lose energy.
So W is work.
So W is work.
Yeah, but how do you lose energy when you put work into a system? Look at our other...
Conservation of energy. I have this marker,
Mm-hmm.
and I exert a force on it over some distance. I do work on it. The energy, I put energy into the marker, and now the marker had kinetic energy.
Yeah.
And it converted that to potential energy and then came back down, kinetic energy, whatever. I did work on the marker. I lost energy.
Yeah, but the marker
system
gained
got
energy.
But the marker gained energy because I was the one doing work on the marker. So whoever's doing the work loses the energy.
So we're only talking about in the cases where the person's doing work on something else. Or the system's doing work on something else.
Yes. When the system does the work. Not when you work on the system, but when the system does work.
What does that look like?
A gas expands. It does work. If I have gas in a piston, so the gas, here's the top of the piston, the gas is right here. And the gas expands and pushes the piston up, so now the piston's up right here. Then the gas did work.
And the gas lost energy.
And so the gas loses energy. And so if it pushed that up, it would do work, it would lose some energy. And if there were nothing else going on in the system, the gas would be a little bit cooler.
Really?
Yes.
So when you lose energy, you get colder?
When you lose energy, your temperature, if you do work, your change in internal energy is negative. So your internal energy goes down. Roughly speaking, temperature is a measure of how much internal energy a system has for the systems that we're talking about.
Okay.
So if a gas does work, the temperature goes down,
That makes
as
sense.
a general rule. And that's how a system can do work. So now let's read this. The change in internal energy of a system, the change in internal energy of a system is equal to the amount of heat that you put into the system minus the amount of work the system does.
The system does. Okay.
Yeah, we're now being a little bit backwards about how we use work. Typically, when we think about, so far when we thought about work, we thought about work being done on the system. We didn't usually think about the work the system does. So for this chapter and the next chapter, remember to think a little bit backwards about work.
Okay.
Because particularly for these types of systems, what we're interested in is the work the system does. You're interested in how much work the piston in your car does, not how much work you do on your piston.
Yeah.
Right? So it happens to be in these cases, when we're talking about thermodynamic systems, we're often much more interested in the work the system does than the work done on the system. So this is always the work the system does. This is always the heat added to the system. Heat added to the system, work done by the system. This is incoming energy, this is outgoing energy. You add heat, you get work.
Add heat, you get work.
Mm-hmm.
Okay.
Makes pretty good sense?
Yeah.
Okay, so that's in a nutshell what this chapter is all about is this equation, conservation of energy,
And just applications of it.
and how we can use that, yeah. Okay, so I guess we can leave that up there, we'll be referencing a lot. Your final energy, that is the weirdest symbol I've ever written, minus your initial energy, which is the same thing as your change in energy, is equal to the amount of heat into the system minus the work coming out of the system. I don't know. Energy going into the system, energy coming out of the system. Trying to think about subscripts I could add to help that make the most sense. Okay. So we talked about one of the ways that we get work out of a system with a piston. So we draw our picture again. We had the gas here, and the piston's like that. The gas expands, pushes up on the piston, and so then it's up here. And so then later our gas looks something like that, right?
Okay.
So the only time that our system can do work is when our volume changes. When the volume changes is the only time that system can do work. It can't do work if the volume doesn't somehow change, the volume of the gas. So when the gas expands, it can do positive work. When the gas contracts, that means you're doing work on the system. Because now if I come and I push down on that piston, and I cause the gas to contract, or compress, now I did work on the system.
Yeah.
So work is associated with volume change when we're talking about gases.
Well, how about pressure and temperature?
Well, I need a pressure to create a volume change, and I can use a temperature to create a volume change. The point is, when the volume changes, then there's a good chance that that gas is either doing work or having work done upon it.
Okay.
Does that make sense?
Yeah.
Okay. So, let's come up really quick with an expression for this. I want to draw a picture of it. We can use just this exact picture right here. So, we'll say it starts out right there. So here's a gas in some piston. And the gas is going to expand. So it's going to start out like that. The gas is going to expand the piston up some distance. And we'll call this distance right here dx.
Okay.
And we'll say that the pressure that was being applied on the piston from the atmosphere, whatever it's in, is P. And we'll say that the area of the cross-sectional area, this is a cylinder, right?
Mm-hmm.
And so you have pressure pushing down. I'll just say pressure times area pushing down and call it the force.
Pressure times area is force.
So you're used to pressure is force over area.
Oh, I see.
Okay, so this cylinder has some cross-sectional area, the piston does,
Mm-hmm.
with some pressure being applied. Together, that's the force that was being applied on top. You good with that?
Yeah.
So if the piston expands from here to here, it had to apply that same force this direction, F this direction, to displace that piston, dx.
Same amount of force?
Yeah.
As the pressure? Well, if it
You
was
have
the
to
same-
overcome the force to move the object.
But if it's the same, then it'll just stay put.
Okay, it's barely, slightly, an infinitesimal more.
Oh.
Okay. And it was just an infinitesimal more to get to start moving. Once you got it moving, then it's the exact same.
Mm-hmm.
Okay. So for a very split second, it was slightly more, and then it was the exact same over this distance. Okay.
Okay.
So the amount of work, the infinitesimal amount of work done over that infinitesimal distance then, is equal to F times dx, right?
Mm-hmm.
Which is equal to, our force is pressure times area. PA dx.
Where's the volume and all that?
Where's the volume in all that? Or more importantly, what's the change in volume in all that? How much did that volume change?
By dx.
Well, that's how much it went up. That's not a change in volume.
It would be A times dx.
A times dx was a change in volume.
So then pressure is directly associated with volume for a change in work?
If you do some work, you have to overcome some pressure.
How about temperature then?
If I increase the temperature of this, then that's me adding heat to the system.
Oh.
If the internal energy of the system doesn't change, and I add heat to the system, then I also have to do the same amount of work.
The system's doing work.
Right, the system has to do the same amount of work. Thank you.
But then wouldn't it move the volume if it's
Yes.
doing work?
Exactly.
That doesn't make sense with your new equation.
With this?
dW, yeah.
Why doesn't it? This is just what dW is. Let me rewrite this equation again. du is equal to dq minus dw. However much work the system does, I have to add the same amount of heat to get it to do that work, assuming the internal energy of the system doesn't change.
Oh, I see. Okay, I'm with you.
Okay, so here's our dW. So if we want to calculate the amount of work done in the system, work then is equal to the integral of pressure PdV from volume 1 to volume 2. Make sense?
V1 to V2 is your change in volume, right?
Your initial volume, your final volume. So whatever your change in volume is. So now, before we erase any of that, we haven't really talked about PV diagrams. I don't know if you've ever seen PV diagrams before.
Lots of diagrams.
PV. P stands for pressure, V stands for volume, PV diagram. And when I draw one of these, it's in reference to an ideal gas. So this is a way for us to plot a bunch of systems of different ideal gases. So these are different volumes, these are different pressures. And if I come and I look at this system right here, it has a certain pressure and it has a certain volume, and I can go plot that somewhere along here. Here it is.
Okay.
So I plot its pressure and its volume. Now you might notice, what about temperature?
Yeah.
Well, notice that temperature is just a function of pressure times volume for a fixed amount of gas. So if the amount of gas you have doesn't change, if I know its pressure and volume, I can figure out its temperature.
Okay.
So now, one of the types of reactions we're going to be very interested in is reactions where the temperature doesn't really change. So imagine that my temperature doesn't change, and I'm just varying the pressure and volume of my gas.
Then they would have to be
For a
in
constant
relation to
temperature.
each other.
Well, I just want to know, what does that look like on this graph?
Well, if P goes up, then V goes down, and vice versa.
Then, perfect. If P goes up, V goes down, and if V goes up, P goes down.
Yes.
If this over here stays constant. That make sense? And so what that's going to look like for a particular temperature is something like this. And so this line represents all the places with a temperature of T1.
Your initial temperature?
Just T1, some temperature. Pick some temperature.
Okay.
Here's all the pressures and volumes that give me that particular temperature. Now, let's say you pick a temperature even higher, T2, and we draw all the points, we map out all the points whose pressure times volume gives you that new temperature. If it's a bigger temperature, then that line's going to be up here, something like this. Here's T2. And T3 would be something like this. I don't know how much these compress together. I'm just drawing rough pictures.
Okay.
And so these are all the points at temperature T3, whatever that is. Here's all the points at T2. Here's all the points at T1.
Mm-hmm.
Good? And so this is what we call a PV diagram. Shows pressure versus volume.
So what it graphs is the temperature.
Well, no, I was just plotting temperature curves on here. Here's all the points at a particular temperature.
Of a particular temperature.
Right, because if I know my pressure, if I know my volume and I know my pressure, I can calculate my temperature as long as n, the number of molecules we're talking about, doesn't change.
So they do graph temperature.
It can graph temperature.
Okay.
I can use it. I mean, I don't know what you mean by graph temperature. There's no temperature axis on here.
Yeah, but it's plotting where.
I'm plotting
Your
all the
temperature
points
is.
where the temperature is the same.
Yeah.
What is that temperature? I don't know. No, tell me what it is. I just know that here's what it would look like for all the temperatures the same.
Okay.
Good?
I see.
Okay. So what is so great about PV diagrams? The great thing about PV diagrams, we can get from this expression right here. Notice that this is our pressure coordinate, and this is our volume coordinate, right?
Mm-hmm.
And so let's say that I have some gas at some temperature T2. So my gas starts out right there. And then over some period of time, let's say the temperature doesn't change, but my pressure drops and my volume increases, but at the same temperature. So my gas starts out right here, and it goes through this process to some point right there, right?
Okay.
Now notice, let's draw a picture of what this particular thing might look like, a physical scenario that might model this. Really quick, let's have a physical scenario that might model that so that this makes sense to you. So how could I get a gas that behaves something like that? So imagine I got this piston right here, and it's compressed like that. With me?
Mm-hmm.
Now, what do? I put it on like a hot plate right here. This hot plate is temperature T2. And let's say the gas was already at temperature T2.
Already at temperature T2?
Already at temperature T2.
So why would you need to put a heat gas under it?
Just stick with me.
Okay.
So that's at T2, and the temperature of this is at T2. So this is our initial point. Here's how we're starting out our system. So our gas starts out at temperature T2, and it's at some volume at some pressure.
Mm-hmm.
So this right here, this is V sub 1, which is our initial volume right here, V sub 1. With me? Now we let this run for some time, and it raises the piston like that. Same amount of gas here, so some of these gas particles spread up there. So now it looks like this, right?
Okay.
Since we did some work, our gas wants to cool down, but since it's on a hot plate, it stays at T2. So the temperature doesn't change.
Does that mean it keeps pushing against the piston?
Well, it keeps pushing to some point. We're going through this exact scenario. So it expands to some point V2. Who cares what it does after this? I'm just setting up that exact scenario.
Okay. So
So it went from V1, which was the volume up to there, to V2. So now this is its new volume, V2, the whole volume.
Mm-hmm.
Since it was on this hot plate, and it's in equilibrium with this hot plate, which is at T2, the gas stayed at temperature T2. So that means we did heat up the gas some. So some energy did flow into the system, and the system did do some work. Because it expanded the volume.
Yes.
Or if you look over here, the volume went from V1 to V2. Notice we got bigger volume. It just so happens our pressure went down, fine, but we got a bigger volume.
Okay.
So now, looking at this, how do we calculate the amount of work done? In a system like this.
Well, from V1 to V2, you would just do V2 minus V1 with respect to pressure.
Times your change in volume.
Pressure here isn't necessarily, pressure is not a constant. Notice that the pressure is changing. Pressure went down.
Oh.
Let me just be very clear. This is not the answer. That is definitely not the answer, because P is a variable. That would be the answer if pressure were constant.
So what is it, P squared over 2?
Well, don't just shoot in the dark.
Well, that's the integral of it.
You don't know what the integral of this is because you need to get rid of that P. You need to rewrite P in terms of V.
Oh, because it's not respective.
It's
pressure.
not a constant. It's a variable.
Okay.
Okay. But geometrically, let's think about this for a second. We have a P and a dV.
Mm-hmm.
Over here, what is P?
Your Y?
Your Y. It's how high up you are.
Yes.
So my pressure at any point is how high up we are. What is my dV? It's an infinitesimal in this direction. So P times dV at any point is going to give me some arbitrarily small rectangle.
What's that rectangle called?
Well, it doesn't matter. The point is, we're going to, this is adding up, an integral is adding up infinitely many of these rectangles.
Yeah, that's right.
And so, this work, geometrically speaking, is
Work.
the area under the curve.
So equals area?
Gives you the area under that curve. Look, when I gave you, when you were, your job was to integrate f of x dx for some function. Here's f of x, who cares what it is? And if you were going from x1 to x2, here's x1, here's x2, geometrically, what did that give you? It gave you the area under the curve.
Yeah.
We have the exact same thing set up there. Pressure, some function in terms of volume, dV, from V1 to V2. Replace your V's with X's, and replace your P with an f of x.
But your P isn't with respect to X or to volume.
Your pressure changes with volume. Your pressure is changing as volume changes. Look, if I were to just give you in a vacuum, no variables, and I say, here's a function,
Okay.
then you know that you can represent that as some sort of f of x.
Yeah.
Here's your pressure. Okay, it's some sort of function in terms of volume.
Okay. Okay.
We'll figure out what exactly that function is, but
You just
I want you to see the geometry here
that is
and
just
how
an
the
integral.
calculus is screaming at you, hey, it's this area.
Yeah.
Okay, you see how the calculus is screaming that? Can you hear it?
Distinctly.
Just a little bit. Okay, that's the beauty of PV diagrams. That's how we calculate the work going from one state to another state with a PV diagram.
Does it just calculate integrals?
It's just the area under the curve. Because here's your work, PdV, and you're adding that up from one volume to the next volume.
Okay.
Good?
I think so.
Now, for our specific case, I gave you more information than just calculate the work done by some random process. Here's the work for any random process. We know something special about our process. I said for our specific case, we stayed at a constant temperature,
Yes.
which we didn't have to stay at a constant temperature. I could have had my curve, any curve written up here, right? I happened to pick a very special case where the temperature stays a constant. Right?
Yes.
Yeah.
So if temperature stays a constant, how can I rewrite pressure? Pressure then is equal to nRT, constant times a constant times a constant,
Over V.
over V. So pressure is a constant over V. So in our specific case here now, here's how you always and forever calculate work.
Mhm.
For our specific case, we can now come plug in, that's the integral from V1 to V2 of nRT over V dV. And now V's our only variable.
And now you can solve
And
it.
now you can integrate the way you know and love.
Okay.
Right.
I see.
And then you solve that. The nRT, we can pull all that out. The integral of V is just natural log of V. So it's going to be the natural log of V2 minus V1, or V2 over V1, same thing.
V2 over V1?
Natural log of V2 minus the natural log of V1 is the same thing as the natural log of V2 over V1.
Okay.
You follow that? Skipped ahead a little. So that happens to be the work for this very specific system I drew. So how do we calculate work in general? That's right here. For our specific case, since temperature was a constant, we knew this relationship.
I see. That makes sense.
So don't get confused by the fact that I calculated work one way and then did it another way. So let me set up another scenario and have us calculate the work.
Okay.
Let's say instead of my gas going from this point to this point, let's say instead, all we did was added barely enough heat to keep the pressure constant. So rather than keeping a constant temperature here, instead we're just going to add barely enough heat to keep the pressure constant as it raises that.
You're saying keep the pressure constant?
Yeah, so now we're just going to try and keep the pressure constant as opposed to keeping the temperature constant. And so we actually need to add more heat to the system. So the system starts out right here, and when it's all said and done, it ends up right here, right? Our pressure stays constant. I'm trying to draw a vertical line here. That wasn't very good. So let's say our gas starts out here and ends here.
So it's the same.
So now the hot plate it's on isn't just at T2. It's on a hot plate that's adding a lot of heat to it. Because the temperature now is going to be way higher than T2. T2 is right here. It's going to have a way higher temperature than just T2.
But the pressure is the
But the
same.
pressure is the same now, because it's a vertical line, right? That's what I'm trying to draw there.
Yeah, I see it.
Horizontal line, thank you. Yeah, that way too much. Okay, now what was the amount of work done going from here to here?
It's just the integral pressure from V1 to V2.
It's just P times your change in pressure, or volume.
It's just P times your change in volume. It's height times
Width.
distance. Width times height.
But it's not a...
So now in this special case, P is constant. Our pressure is now constant.
Oh.
So just pull out the
Yeah,
P.
I see.
And you get P times the integral of dV is just V from V2 to V2 minus V1, so V2 minus V1. It's just a rectangle. Doesn't get simpler than that.
Yeah.
Okay.
That doesn't seem okay.
So we just barely calculated the work done with two different transitions and systems. So here's always and forever how you calculate the work. And then depending on your specific circumstances, how that's going to come out is going to change. And I gave you two different examples.
What happens if your volume is the same?
Then no work's done.
So no work's done?
Volume means you went from somewhere like right here to somewhere like right here. What's the area under that curve?
But your pressure changed.
Yeah, but no work was done.
But wouldn't that have an effect on the system, even if no work was done?
Sure.
I'm saying
Well,
in a
how do you contrive so that this can happen? I mean, the way that you're making something like that happen is you're somehow getting heat to just leave the system. You're like letting it cool down.
Yeah.
So this is what would happen if you just let it cool down. So your work out is 0, but your heat in is negative. You're not adding heat, you're extracting heat.
Oh.
And so your energy, internal energy, is going down, and hence your temperature is going down.
I see. That makes sense.
Okay. So now that we did all that, that was a good step into, good way to get our foot in the door. Let's do the first example. Isothermal. Did we already talk about isothermal?
Nope.
But then he just barely mentions it. All right, let me write all 4 of them up here somewhere, and then we'll talk about each one as they come up.
Or is the laws?
No, 4 common conditions. Sorry, it'll make sense as I say them, and then you'll understand why I said it.
Okay.
So he specifically said isothermal. So we'll write isothermal first. Don't go past that because isothermal means temperature equals a constant. Your temperature doesn't change. That means isothermal. So the first time when we calculated work, that was an isothermal reaction. The temperature didn't change. At the start it was T2. At the end it was T2. That was isothermal.
Okay.
What does ISO mean?
Iso, not changing.
Like an isosceles? Maybe.
Same,
Same.
probably same somehow. So same thermal, same temperature. Okay, so isothermal, that's constant temperature. Isobaric.
So okay.
Uh-huh.
Is that same pressure?
Which is constant pressure. Yes, so that's when your pressure is a constant. So we showed the work on those two.
Mm-hmm.
And then we have isochoric. You can probably guess what that is.
Well, what does choric mean?
Doesn't matter. What else have we not said needs to stay constant?
Same volume.
Volume. Volume equals a constant. Isochoric. And then our last one is adiabatic. Adiabatic means the heat we add to the system is 0. No heat added.
But there still could have been work, right?
Yep, there still could have been work, just no heat added.
And these are just different cases of that law?
These aren't cases of law, these are just different types of processes we're interested in. We're interested in some process where the temperature doesn't change. We're interested in some process where the pressure doesn't change. We're interested in some where the volume doesn't change. And we're interested in some where we don't add any heat to the system. And so these are 4 types of processes that we have general interest in. And so we'll need to know how to calculate the work in all these different cases. We already calculated the work here, we calculated the work here, we calculated the work here, we just haven't done this one.
Okay.
What was the work here?
0.
0, okay. Just making sure you remember, we did calculate that even though we didn't write anything.
ISO means 4.
Equal?
Same.
Same.
They're equal. They're ISO.
Okay. So now I was going to do the first example problem. Erase all that. And maybe can put our more permanent stuff over here. So we also had our first law of thermodynamics, that was delta U is equal to the amount of heat added to the system minus the amount of work done by a system, or an infinitesimal change in U is equal to an infinitesimal change in heat minus an infinitesimal change in work.
Yeah.
Okay. And maybe to the left of these, calculate their works. So for isothermal, we calculated that the work was equal to nRT times the natural log of V2 over V1. For isobaric, work was just equal to P times V2 minus V1. For isochoric, work was equal to 0. And then adiabatic, we haven't calculated the work in that case yet. So, little summary of everything we have so far. Now let's do the example problem. An ideal gas undergoes an isothermal expansion at temperature T. Its volume changes from V1 to V2. How much work does the gas do?
So just plug in V2 and V1.
Yeah. So it's trying to get us to derive that equation, and we already did that. So the first example just has us derive that equation. Maybe we'll write it one more time, rederive it, cement it in your head. So I know work always and forever is equal to V1 to V2 of pressure times dV. Always and forever, that's what it is. Mm-hmm. We were told that we're dealing with an isothermal expansion, and that's an ideal gas. In an ideal gas, PV is equal to nRT. If T is a constant, then I know that P is equal to nRT over V. And so we get work is equal to nRT times the integral from V1 to V2 of dV over V, which is equal to nRT times the natural log of V2 over V1. Right?
Yeah.
Another way that we could write this, maybe this is worth pointing out. Imagine you don't know your volumes, you only know your pressures. You with me?
Well, then you can solve for volume.
Yeah, we can solve for it, but we'll just plug it, we'll create a formula that uses it.
Okay.
So notice that in an isothermal reaction, if T is a constant, then this whole thing is a constant, so P times V is always a constant. Which means your pressure at time 1 times your volume at times 1 has to equal your pressure at times 2 times your volume at times 2. Right?
Yep.
Yeah.
Which means, if I put my V1 over here, my P2 over here, I get P1 over P2 is equal to V2 over V1. You see that?
Mm-hmm.
And so another way that we can write this exact equation is, nRT times the natural log now of P1 over P2. Flips. Because that's the same number.
Oh.
So, could be useful to have it that way. Maybe not. Okay. So we've already talked a bit about the geometry of PV diagrams to calculate the amount of work done. Now we're also often going to be interested in cycles. So let's say that I have some cycle that I keep putting my gas through over and over and over again. And so my gas starts out here, and then I isothermally expand it to there. Step 1. Step 2 is we then compress it at a constant pressure back to here. And then we add heat to the system, keeping the volume the same to get it back up to temperature here. So it goes around like that. And then we repeat the process.
And the system just does it over and over?
Well, we have to add heat to the system to keep it doing this, and the system's going to do work as we do this. Roughly what a car engine does. We'll get more into specifically a car engine.
Okay.
But roughly speaking, here's what engines do. They absorb heat and do work.
Yeah.
Right? And so what's the total work done in one cycle?
Total work done in one cycle?
Yes.
0.
Not 0. So the work we do, and it's kind of making a mess of that picture there. I'm going to draw something similar over here, just bigger, so that we can hopefully see it better. Okay. Here's my loop, right?
Yes.
Now the amount of work the system does going from point A to point B, and we'll call that point C. So going from point A to point B, the amount of work it does is this area under the curve in between those 2 points, right?
Okay.
So that was it going from here to here, right?
Mm-hmm.
So the volume expanded. Now I compress this thing, keeping the pressure constant while I compress it.
Okay.
With me? How much work does the system do? Negative this area. Because you're doing work on the system now. The system isn't the one doing the work.
How do you
The
compress?
system does work when it expands. You do work on the system when it compresses.
How can you compress without changing pressure?
You let some heat seep out as you do it. So, as you let the gas just sit there, it's going to cool down, right? Which is naturally going to want to make the pressure drop.
Yeah.
So then you push a little bit. Keep the pressure same. It cools down low, you push more. Cools down low, you push more. Cools down low, you push more.
Okay.
One way you can do it. But don't get too caught up in the details of how we can make these reactions occur versus just assume that we're able to come up with some way to do the reaction. The important part is going from here to here, we do work on the system, so the system does negative work underneath that curve.
Yeah, I see it.
That make sense? And then going from here to here, how much work is done on the system?
There's no work.
Or how much work does the system do? 0. And so total, the amount of work on this loop is the area under this triangular portion.
How do you find that?
How do you find that? You do this work minus this work. We know how to calculate this work,
Mm-hmm.
right? So the work from A to B we know is that we assumed, if we follow the picture I had here, we assumed that that was an isothermal reaction.
Yeah.
So the work there is then going to be, our isothermal reaction is right here, and RT times the natural log of V2 minus V1, right?
Okay.
And then the work from B to C is equal to negative, since we're going that way. And it's going to be, we keep a constant pressure. The pressure is the same as the pressure we had at the end, which was P2, times V2 minus V1.
Okay.
And so this plus this is our total work.
That makes sense.
Now notice, we could have blindly just used this formula for this part right here, and it would have worked as well. If we remember that the formula is your ending volume minus your start volume, right?
Mm-hmm.
Over here, our ending volume was V1, and our start volume was V2. So the way that we could have calculated the work for this reaction right here, we could have said that the work from B to C is equal to the pressure there, P2, times our ending volume, which in this case is V1, minus our starting volume, V2. And we could have blindly used the formula. Notice that this is the same as this.
Yeah, because V1 will end up being negative, right?
Well, just multiply that by a negative, or factor a negative out of this. And it just flips those around.
Gotcha.
So you can blindly use these equations, and they'll guide you right,
Okay. What do you mean
And
by
the-
blindly?
without thinking about whether was the system doing work, or us doing work on the system. See, here we kind of reason through to get this equation rather than blindly plugging in. This is blindly plugging in. Take your pressure, your ending volume minus your starting volume, without even thinking about it, as we mean by blindly.
Okay.
Rather than we stopped and we thought and we reasoned our way to that equation. So, whichever floats your boat. There's a right or wrong way. It's just, for me personally, I'm very often going to do stuff like this as opposed to that, and so I don't need to think that you somehow need to remember, oh, this is equation, well, that only works when the system's doing positive work, and it doesn't work when it's doing negative work. No, this always works. And I'm just thinking to come up with this rather than just plugging in.
Okay.
That's why I don't like feedback.
So what is this type of work called then?
Well, that's just a network done in this cycle.
Network done in the cycle?
So we started here. From here to here, the system did this much work. And then from here to here, the system did this much work. And from here to here, the system did no work. We're back to where we started. And yet the system did positive work.
Okay. Yeah.
Good?
Gotcha.
Okay, so now we come to a very important point. And the important point is, it doesn't make sense to talk about how much work is in a system.
Why not?
We just barely took a system, we took it through some cycle, and now it's back exactly where it started. And it did some work. So if it had some amount of work that it has right here, and then I take it through some loop, shouldn't it have the same amount of work again? If work made sense to talk about in this way?
Well, yeah, if you put it like that, I mean, obviously not.
Obviously not. Well, you say obviously not, but notice that something like temperature is somehow conserved through this process. Whatever the temperature is here, no matter what loop I send it on, when I get back to that same point, we have the exact same temperature again.
And
Temperature is a state variable. Pressure is a state variable. Volume is a state variable. If we get back to where we started, we have the same pressure, we have the same temperature, we have the same volume.
So work wasn't done.
Work was done. Work is not a state variable. It makes sense to ask how much volume does a system have. It does not make sense to ask how much work does a system have.
But it makes sense to say how much work was put in or taken out.
How much work a system did over some cycle, sure. But to just look at a system and say it has this much work, that makes no sense.
But you can look at a system and it says it has this much heat or this much energy.
Energy and heat are not the same thing. Heat is energy and transfer. So once again, looking at this loop, as this system did work, it also absorbed energy. It absorbed heat. By the time it got back where it started, it absorbed heat.
What do you mean by absorbed? The temperature.
Heat went into the system.
Yes, but also went out.
No heat went out of the system. The system did work.
System did work. Okay,
The system did work.
gotcha.
And heat was added to the system.
Yes.
No heat was taken out of the system. Heat was only added to the system, and the system did work.
What about when it cooled down?
What about when it cooled down? Oh, I see what you're saying. You're saying this part right here, we can view that as cooling down. So we can say, okay, some heat left the system here, but more heat went into the system here. So in the aggregate, heat was added.
Didn't the exact same?
No. Otherwise, we couldn't have done work.
But it's the same temperature.
Look, when we take this thing on a loop from start to finish, what is its change in internal energy?
The double heat minus the work. Or they
The change in energy is zero in its internal energy. If I take the gas, and then you close your eyes, and I do all these weird things with the gas, and then when it's all said and done, I leave the gases right back exactly where it started. Then the net change in internal energy is zero.
Mm-hmm.
You with me?
Yeah.
Now maybe while you close your eyes, I took the gas through the cycle, maybe I didn't. There's no way for you to know. Because the gas is now back to an identical state.
Okay.
So the internal change in energy, the change in internal energy is zero.
Yeah, that makes sense.
the work, it did some work. So we had to also put some heat in there.
But you're going from temperature 2 to temperature 1 and then back to temperature 2.
Right. And so the heat that we put into the system going from here to here has to be greater than the heat lost going from here to here.
But it's the same.
How would you know whether or not that's the same?
Because it's going from T2 to T1.
Changing the temperature is not the same regardless of the pressure.
What do you mean?
As pressure increases, wow, how do I even say this? I'm not sure the right way to say this to you yet. Maybe we'll see with example problems. We're getting lost in talking about details of this. I don't know a better way to say it to you. Stop trying to maybe let your intuition go for a second. So, letting a gas cool down from temperature 2 to temperature 1, keeping it at a constant pressure. Here's maybe the way I can say it. The lower the pressure is in a system, the easier it is to change its temperature. Okay, so since this is all at a lower pressure, then the amount of heat we need to take out of the system to lower its temperature is less than the amount of heat we add here because the pressure keeps increasing as we go. And so it takes more joules to create the same amount of temperature increase. So it might only take us 10 joules to get our first degree increase, but it might take us 20 joules to get our next degree increase. You're used to 1 joule should always give you the same amount of heat increase, but that's when we were doing things like heating up water. Not an ideal gas. And it doesn't make sense to just talk about the heat capacity of an ideal gas. When we talk about the heat capacity of an ideal gas, then you'll notice that it has, there's two, we've only talked about one so far. It was C sub V, and C sub V meaning if we keep it at a constant volume. Then here's a T capacity. But a gas doesn't in general just have a heat capacity. Okay. So anyways, if we went through this loop here, then we definitely did some work. So we definitely did some work, so we have some value here, work W. And so if we definitely did some work, then we definitely had to add some heat to the system to account for that work. If we're back where we started. Does that make sense? So we're back where we started. So our internal energy is back to what it was. Our temperature is back to what it was. Our pressure is back to what it was. Our volume is back to what it was. On that loop. However, we got some work out of the system, and we added some heat to that system. And so this is why it doesn't make sense to talk about the amount of heat in a system as well. Because I can have a system at some point, take it on a loop, now it's back exactly where it was, and I added heat to the system. And I can keep sending on this loop as many times as I want, adding heat to the system forever. Without subtracting heat from the system. And so if it made sense to talk about the heat of a system, then the heat of the system would have to keep going up, which it doesn't.
Okay.
Does that make sense? So heat and work are not state variables. They don't tell you about the state of a gas. It doesn't make sense to say this gas has this much heat or this gas has this much work. It does make sense to talk about its temperature. It does make sense to talk about its internal energy. It does make sense to talk about its volume. It does make sense to talk about its pressure. Those are state variables. They tell you about the state of the gas.
So your state variable is defined by those other two?
So heat and work are related in this way such that their difference gives us a change in a state variable. And so their difference is going to be some conserved quantity.
Gotcha.
So just want to stress that because when kids first start studying thermodynamics, it's really hard for them to get down their heads the difference between temperature and heat. So that's why I'm stressing it if it feels like I'm overstressing it. All right, so then the author finally introduces you to the actual law of thermodynamics, first law of thermodynamics, which we have written right here, or the infinitesimal version right there.
Okay.
He has an interesting little cycle now that he uses, not one like this, but just for a typical person going throughout their day. So in the author trying to explain, well, here's what he says. He says, let's imagine that we have a person, and at the start and at the end of the day, they've done exactly as much work as calories they've consumed. So he sets up some hypothetical cycle. He starts out with the person, they sleep for 8 hours, and during that time, we'll imagine that they do 2 million joules worth of work, sleeping, to heat up their body and whatever else. Mm-hmm. And then they stop in first hour of the day, they eat breakfast, so they consume 5 million joules. And that in that time, because you know, as you eat your food, you're still heating, you got to chew your food, all that. Then he says the work they do is probably 0.7 million joules. And so he gives you a typical cycle of someone's day, and so how we can create calculations for roughly how many calories should a person consume in a day.
And we know that, right?
And we can make rough calculations, varies from person to person and how you live, but you could create a rough estimation of how many calories you need to consume in a day. How do we make that calculation? We basically need to track how much work you do in a day.
Oh, so it depends on the person.
Huh?
Is it like 2,000 calories?
I don't know what it is. 2,000 sounds roughly right.
2,000 is what all the doctors recommend.
But it should vary a lot with the person. For example, a bigger person with more surface area radiates more heat. But then at the same time, a bigger body also is better at storing heat. So I don't know if that comes out in a net positive or a net negative.
Yeah, that makes sense.
Or maybe even don't think about bigger versus smaller, think about a short person versus a tall person. I guess in that case, it's pretty obvious a tall person needs a good amount more food than a short person. Because then they have a good amount of surface area increase without a bulk increase of much.
Yeah.
And so stuff like that. And you can see how just how you're physically laid out could already account for a lot of things. And then some people might just, I don't know, naturally burn hotter.
Or depending on the activity they do, right?
Yeah, and we haven't even talked about physical activity yet. We're just talking about, let's just lay down the difference between yours and my biology before we even talk about how we actually choose to live our lives differently. Because my natural internal temperature might be, I don't know, 98.9, where yours might be 98.4. Mm-hmm. The average is just 98.6. Maybe I burn a little hot, maybe you burn a little cold. And how much does that account? I don't know. And so there could be a lot of things that factor into that.
It's kind of interesting.
Yeah, it is interesting to try and come up with a precise calculation on some of those for a particular person.
And you probably could, right?
I would assume so. I just don't think anyone ever thinks it's really worth the effort. But I don't see why you couldn't. Okay, let's do the next example. You propose to climb several flights of stairs to work off the energy you took in by eating a 900-calorie hot fudge sundae.
Okay.
So,
Is this the small calorie or the big calorie?
big calorie, I assume. That's usually what we mean with food, is kilocalories. So you ate a nice big hot fudge sundae, and it said on that, warning, 900 calories, and you ate it anyways. You
So
crazy
this
guy.
is like a weight loss routine?
Yep.
Like
Well-
you would do this math for weight loss
Oh.
routines?
Sure. So Q, the amount of energy that you're plugging into yourself, is 900 calories. And I assume it's calories. Capital C. Skipped ahead. 2. Okay. how high must you climb upstairs to lose those 900 calories, assuming that your mass is 60 kilograms? So we assume that your mass is 60 kilograms, and now you've got to burn off 900 calories.
Okay.
Now 900 calories, when we convert that to joules, I think it's 4.16 joules per calorie.
4.186.
4.186. Okay. So we have 900 times 1,000 gives calories times 4.186, and that gives us 3.77 times 10 to 6. Joules of energy that you now have available to you. Right?
GPUs, right?
To use, right?
Okay.
And so how do we calculate how much energy you get for lifting?
Force times distance,
Isn't it?
Force times distance,
which is mass acceleration distance.
which is, what's the
Isn't it
acceleration?
just potential
Potential energy? Yes.
of gravity.
You need to increase your potential energy by this much. What's the equation for that?
Wait,
Come on, just think about it. You've already got it. Work. You said force times distance. Okay, the distance is going to be h. That's how high up we go. What's the force?
Gravity,
Gravity. That's the acceleration.
mg.
mgh. Come on.
Yeah, that's the potential.
Okay,
Potential
potential
energy.
energy.
Duh.
mgh. The work.
Yes.
Force times distance.
Okay.
You should be able to come up with that.
Yeah.
And we need this to equal Q.
Okay.
That's how high you need to go to burn Q calories. So we take Q and we divide it by your mass times gravity. And we get that you need to go up 6,400 meters.
It's gonna be a long day.
Roughly 6,410 meters. So H is roughly 6,410 meters. Let's see what the author gets. 6,410. Okay. Now, you do not really need to go this high to burn off that many calories, because this is just assuming the potential energy. There's a lot of things that also go into you walking up the stairs. For one, your body heats up from all your motion, and so you're going to give off a lot more heat. Your body's going to start sweating. That sweat, that water on your surface, is going to absorb heat out of you as it goes off. Right?
Yeah.
And so a lot goes into it, and so you're not going to need to go near that high to actually burn off that many calories. So it's going to be much less than that, probably closer to like 2,000 meters. But still a lot. That's still a ton of energy.
Yeah.
But just don't take that at face value. If you went that high, you would have definitely burned off that much energy and then some.
Gotcha.
So if you want to be guaranteed to be rid of that someday, you just have to go that high. And then you're guaranteed to be rid of it. But I would guess half to a third that would also work. Just a button.
Yeah, I was going to mention it.
Kind of, yeah.
Well, you were in the middle of everything. I didn't want to stop you to fix a button.
All right. Let's do another one, I guess. Okay, this one references some diagrams, so let me draw the diagram really quick. So we got a PV diagram. We got 2 points on it, and the top curve is going away and the bottom towards. So roughly what the author has drawn is that's going towards, that's going away, and my picture might be lying a little bit. And then just mark some points. This is point A, this is point B, this is a volume at A, this is a volume at B, I did lowercase a, volume at A, volume at B, this is the pressure at A, and this is the pressure at B. Okay, so That figure shows a PV diagram for a cyclic process in which the initial and final states of some thermodynamic system are the same. So it goes on some loop, so the initial and final state are the same. Starts where it ends.
Okay.
As shown, the state of the system starts at point A and proceeds counterclockwise in the PV diagram to point B, then back to A. The total work is negative 500 joules. So if we were to calculate the area, here, when we go from here to here, we get the area under this curve. When we go from here to here, we get the negative of the area under this curve.
Mm-hmm.
The difference then, they're saying the work on the cycle is going to be minus 500 joules. So that's 500 is the area inside of here.
Gotcha. That makes sense.
Why is the work negative? Why is the work negative? Because the work done on the system to get it back here is greater than the work done by the system to get it over here.
Yeah.
So the net work by the system is negative. B, find the change in the internal energy and the heat added during the process. So here's W. Our job is to find the heat added, Q, and the change in our internal energy.
So we first find Q?
Well, how can we figure out Q if we don't know the change in the internal energy? And how can we figure out the change in the internal energy if we don't know Q?
Yeah.
Yeah, so we're stuck. Unless you remember something I told you about U.
It's 0.
It's 0. U is a state variable. If you're back where you started, your total change is 0. And so then the heat added has to be 500. Where and how is the heat added? We don't care. The heat added has to be 500. Because that's the work we got out of it. Make sense?
Okay.
Do you use the same unit for work and Q? Just joules?
Yes, it's all energy. Change in energy is equal to energy in minus energy out.
Okay.
That's one way you could read that. And I probably shouldn't say it that way. I shouldn't say energy in versus energy out, because it's possible to add energy to a system by doing negative work on the system. And it's also to take energy out of the system by cooling it down.
Yeah.
So don't take that too literally. All the heat, all the energy coming into the system isn't necessarily through heat. If I can press a gas really quick, the gas heats up. Right?
Well, wouldn't that be adding heat to the system?
No. That'd be me doing work on the system. No heat was added.
But that still creates heat?
It increases temperature. It doesn't create heat. It increases temperature. You can increase temperature without adding heat to a system. You can press it really fast.
That makes sense.
No heat added.
Okay.
Okay. Just really quick, give you intuition for that. So imagine that my gas is right here.
Yes.
Well, no, that's still not going to work. Sorry. It's not going to be good intuition like I thought. What'll that be? Okay. So, and then we've already done that. Let's do one more of these. 1 gram of water, which is 1 cubic centimeter, becomes 1,671 cubic centimeters of steam when boiled at a constant pressure of 1 atmosphere. Okay, this is a great one because it teaches you steam engines. How does a steam engine work?
You keep the pressure the same and you add heat?
It ultimately boils down to the idea that if I've got some piston in here, here's my piston, right? And inside of here, I've got some water. And if I turn all that water to steam, what's going to happen?
It's gonna create pressure.
That water is going to expand,
Yes.
which is then going to create pressure as it turns from water to steam. So ultimately, a steam engine relies on the fact that when you turn water to steam, it expands. That expansion creates pressure, which then can create work.
Yeah.
And then you can use that work to turn your wheels or whatever you're doing, like on a train.
Trains use steam engines?
Old trains do.
That's cool.
The ones where you see them shoveling coal into the furnace.
Yeah.
The coal, that's basically them, that's right here, underneath the water, essentially. You add coal here, you're burning it, which is adding heat to the water, turning it to steam, expanding, pushing up on a piston, and then when it pushes up on the piston, you have that hooked to some system which pushes the wheel back. It pushes back on the wheel,
Yeah.
causing the wheel to start turning. So yeah, steam engine. The Titanic used a steam engine. So, steam engine, one of the earliest engines.
How does
So-
it come back down?
Huh?
How does it come back down after the steam pulls it out?
Oh, there's ways for it to be released. So, what you essentially have is, as it expands up, you have holes up right here and right here for steam to get out and fresh air to get in, which doesn't have the steam. We'll get into, not specifics of a steam engine, but we'll get into more specifics of an actual car engine and what a car engine does. Basic same process.
Do they have to add a lot of water to that?
Well, let's get a feel for this with this example problem. So in this example problem, we're going to be taking 1 cubic centimeter of water. Our water is going to be 1 cubic centimeter. And we're going to convert that to steam. And when we convert it to steam, 1 cubic centimeter of water now has 1,671 cubic centimeters of steam. That's the expansion ratio,
Wow. Okay.
which is massive.
Can't you compress steam into 1 centimeter?
Yes, so this is assuming that our pressure is equal to 1 atmosphere. At 1 atmosphere, if you convert water to steam, here's your expansion ratio. And you notice this all the time. You have a boiling pot, the lid's on top, a little bit of water turns to steam, and it pushes the lid.
Yeah.
It's happening all the time. Water is very slowly being turned to steam, and that steam's bubbling out of your pan.
Yeah, but not at that rate.
Well, you're not turning a whole cubic centimeter of water to steam like that. You're very gradually turning a teeny bit of water to steam.
Yeah.
That's true, but that's like almost 2 full meters cubed.
No, no, no.
Why is it not?
How many cubic centimeters are in a cubic meter?
10,000?
Try again.
1,000?
Try again.
100,000?
Try again. 1 million.
1 million? Oh my god.
100 centimeters cubed is 1 cubic meter. That's 1 meter times 1 meter times 1 meter.
Oh, I see.
Okay. That is not close to 2 cubic meters. That is almost 2 1,000ths of a cubic meter. Right? 0.2%.
That makes a lot more sense.
Okay. Alright. But still a massive expansion ratio.
Yeah.
It's occupying 1,671 times the amount of volume it was before. Okay. Oh, example problem. The heat of vaporization at this pressure is 2.256 times 10 to the 6. So the heat of vaporization, I forgot the number.
L sub V.
L sub B 2.256. I think it's times 10 to 6 joules per kilogram.
That'll be what?
Yeah, what is L sub V?
We used, you remember, we talked about 2 processes. So going back and we talked about heating up water. And we said, so don't get confused, this now is temperature versus heat for water.
Temperature versus heat.
Mm-hmm.
Okay.
So I'm going to add heat and the temperature is going to go up.
Okay.
And I'm going to put on here 0 degrees Celsius. Here's 0 degrees Celsius. And here is, I don't know, 100. You with me?
Mm-hmm.
So we're going to start out with some ice, and the ice is going to start out this cold.
Okay.
Negative 20 or whatever. As we add heat, the ice gets up to freezing point, or melting point. And then we got to convert all the ice to water. And then we heat up all the water and get it hot enough, get it up to 100 degrees Celsius, and then we turn all the water to steam. And then we can heat up the steam and get the steam hotter.
Okay.
And going from here to here, we use the heat capacity of ice. And going from here to here, we use the heat capacity of water. And going from here to here, we use the heat capacity of steam, which we can't really talk about because steam doesn't really have a good heat capacity. But what about the amount of heat it takes to go from here to here, or from here to here? That's where you saw L. You had L of vaporization for here, and then L of, I can't remember what we called it here, but L of melting or something like that for here.
For water.
For any substance. I drew one for water, but for any substance. So when we're calculating the amount of heat for this or for this, then that equation was Q is equal to MC, mass times some constant, times your change in temperature that you're after. Right?
Mm-hmm.
And then, so that was for heating up a material, but when you're actually changing it from one phase to another, then that was Q is equal to, and rather than C, we just had M times L. And it doesn't depend on temperature because the temperature doesn't change as you're converting water to steam, or as you're converting ice to water. So in our case, we're using an L of vaporization because we're talking about up here, rather than an L of, I can't remember what's called down here, L of melting or whatever.
Okay. Yeah, I'm with you.
Okay, so 1 cubic centimeter of water is also 1 gram of water.
1 centimeter is equal to 1 gram.
1 cubic centimeter of water weighs 1 gram.
It's equal to, okay.
So I know that our mass now is equal to 0.001 kilograms. 1/1000th of a kilogram.
Mm-hmm.
Okay, so that's the mass that we're dealing with. And we know our L, so I can figure out how much heat it takes to convert 1 cubic centimeter of water to steam.
Yeah, I see.
Okay, now I'm not sure what the problem's asking us to do yet, but that's that. Compute A, the work done by the water when it vaporizes, and B, its increase in internal energy. Okay, so as the water vaporizes, the volume changes a lot.
Yeah, by that much.
By that much. So, our work, the amount of work the water does, is equal to the integral of our initial volume to our final volume of our pressure dV, right?
But your pressure is constant.
Our pressure in this case, we're going to assume is constant. Perfect. So it's going to be pressure times our ending volume minus our initial volume. That's going to be our work,
Mm-hmm.
right?
So your work is just 1,670?
Well, hold on. That's cubic centimeters. If we got to convert to meters to get joules.
But volume is,
We got to convert our volume to cubic meters.
cubic meters.
Yes.
Oh.
So that we can get to joules. What is a joule?
A joule is kilograms over meters.
It's kilograms meters squared per second squared. And so you have to get to meters if you want to get joules when it's all said and done.
Okay. I'm with you.
Okay. Okay. So there's the work that we did. Now we're looking for our change in internal energy of our system,
Yes.
right?
Mm-hmm.
So, delta U is equal to the amount of heat minus the work that we do.
Okay.
So then you plug in your
So what is our heat?
mass times L, which we know.
Our heat we get from this, and then we subtract away our work, and that gives us our change in energy.
Okay, I see.
Make sense?
Mm-hmm.
So, we can calculate this. 1 atmosphere, we need to get that in terms of pascals. That's 1.013 times 10 to the 5. So calculating the work, 1.013 times 10 to the 5, that's our pressure, times now our change in volume. Our final volume is 1671 divided by 1 million minus 1 divided by 1 million.
That's how you get cubic meters?
It's one way to do it. And so when that's all said and done, we get 167. So the work done, this is approximately 167 joules. And then calculate this here. We need to take 1/1000th. Well, that one's obvious because we're just reducing that by 1,000. If I take L and I multiply it by 1/1000th, then we're going to get Q is approximately 2.256 times 10 to the 3 joules. Right?
So that's 2256.
So just 2256. And so our change in internal energy is just the difference of those two numbers. Which comes out to 2,087 joules. 2,087 joules. Okay, we did it right. Make sense?
Yeah, all except your 1 million. But what's another way that you would calculate or find your cubic meters?
Convert each one of those cubic centimeters to meters. And so I need to multiply it by, so I have 1671 centimeters cubed. I need meters cubed.
Mm-hmm.
So I need to multiply this by 1 meter. If I'm going to multiply by a meter, I need to divide by a meter 3 times.
3 times. Okay, I see. Okay. So it's just like doing simple chemistry.
It's exactly like doing simple chemistry.
Okay.
There, you now know chemistry. Convert units.
Yeah. Okay.
Okay. Kinds of thermodynamic processes. We've talked about these a little bit. An adiabatic process is the first one that they mentioned. An adiabatic process, that's where no heat is added to the system. So your change in U is equal to the negative of how much work you do. Specifically for adiabatic processes. So that's the extra information you have from those. For an isochoric process, that's the one with constant volume. So if you have constant volume here, then you know that your work is always 0.
Mm-hmm.
And so in that case, then you always know that your change in internal energy is just equal to the amount of heat added to the system.
Oh, that makes sense.
For isobaric process, an isobaric process, we can have both heat and work, but here's how we calculate the work. Isobaric means constant pressure. And then finally, isothermal. An isothermal process, for the cases that we're dealing with, isothermal process means that the temperature stays constant, means that the internal energy of the system doesn't change. So for an isothermal process, Q is equal to work. Because our change in internal energy is 0.
Gotcha.
So remember, temperature is somehow a gauge of how much energy is in the system. So for isothermal processes, our work is equal to our energy. Our change in internal energy is 0. For an ideal gas. And so for an ideal gas, I'll just read it to you rather than writing this somewhere. So the author makes a specific note. It's in one of his yellow boxes to mark that. It's very important. The internal energy of an ideal gas depends only on its temperature, not on its pressure or volume. So when we're talking about an ideal gas, its internal energy, or U, depends only on the temperature. So if the temperature stays constant, U didn't change.
Gotcha.
And so then your heat's equal to your work. That's the best way to say that.
What if you compress it really fast?
What if you compress it really fast? Then the temperature shoots up. That's not an isothermal process.
Okay.
Okay. All right. Now back to talking about heat capacity. Heat capacities for an ideal gas. Now we already talked about heat capacity for an ideal gas before, but there was an unspoken assumption in everything that we were talking about, and that is that the gas we were heating up, the volume was staying constant. So before, when we were talking about capital C, our molar heat capacity, we should have been putting a sub V there to remind us that this is when the volume stays constant.
Okay.
So everything that we did with like kinetic theory, and when we were calculating how much energy goes where, and talking about our heat capacities, we were always talking about this heat capacity. And we found out for monatomic gases, then it was 3/2 R. For diatomic gases, it was roughly 5/2 R. And for solids, it was roughly 3 R. Now notice with solids, their volume doesn't really change, and so.
Yeah.
But for gases, their volume can change. So this was their heat capacity when we were keeping them in a constant volume. This was for monatomic gases, this was for diatomic gases. Is this ringing some bells?
Yes.
And then it got a lot more complicated really quick for higher level gases. Okay. So molar heat capacity. Now that's with the constant volume. Now imagine that we allow the volume to change. How do we expect that to affect the heat capacity? So now I've got heat in some piston. It starts out right here, and I've got my gas in here. And now imagine that I don't require the volume to stay there. And now the volume can actually move some. And so let's instead think about if we just keep the pressure constant.
Keep the pressure constant.
So all we're going to require now is that the pressure stays constant as opposed to keeping the volume constant.
Okay.
So as we heat up the gas, what's going to happen? If this piston at the top now can move,
Then it'll move. a
then
lot
it will
faster.
move the piston up some. So then the piston will move up to here. And so the gas is going to do some work.
Okay.
See, before, if I don't allow the piston to move, and I heat up the gas, then all the heat I put into the system goes into making those gas particles jiggle around faster.
Yes.
Or in other words, all the heat I put into the system goes into raising the temperature. But now if I don't keep the volume constant, and I instead just keep the pressure constant, then as I add heat, the volume can change. And so the gas might be able to do some work. So some of the energy I put into the system goes into heating up the gas, but some of the energy I put into the system is also going to go into doing some work.
Yeah, that makes
And so I may have to put more energy into the system to get the same raise in temperature.
To get the same raise in temperature
Yes,
as what?
as what we have here. So over here where my gas is contained to this volume, it can't change.
Gotcha.
And imagine it takes me 100 joules of energy to raise this one by 1 degree Celsius.
Okay.
Now I come over here and I add 100 degrees, I add 100 joules.
It just moved the
It
volume.
would raise it by 1 degree Celsius if I didn't let that lid move. But since I let that lid move, some of the energy goes into moving the lid, and some of the energy goes into heating up the gas. Not all the energy I add to the system is going directly into heating up the gas now.
Okay.
Some of the energy goes to doing work. So now I'm going to have to add more heat than before to get the same temperature change.
Doesn't that always just make it go up more?
Well, I could also make it increase the temperature. We're just keeping constant pressure.
Okay, so this is the case when it's a constant pressure. How about when pressure isn't constant and volume isn't constant?
And then heat capacities are all over the place. And to talk about the heat capacity of a gas is a nightmare. So we're only going to talk about it in two simple scenarios. With our PV diagrams, we're going to be interested in when we keep the volume constant and when we keep the pressure constant. And that's it.
Oh, so we did the first part, now we're gonna, I got you.
Yes. So we already figured out when you keep the volume constant, here it is. Monatomic gas, diatomic gas.
Okay.
When we keep the pressure constant, however, we expect the number to be bigger.
Yeah.
Could be,
Yes, so I expect this to be bigger than just CV, more than CV,
why is that?
because some of the energy is now going to go into doing work. When the volume was constant, all the energy I add to the system goes to increasing the temperature of the system, or to increasing the internal energy of the system.
Mm-hmm.
Now, if the volume isn't constant, then when I put energy into the system, some of that energy is going to go into heating up the gas, but some of it is also going to go into doing work. And so now not all my energy is going into heating up the gas.
So you,
Only some is.
you would have to put in more?
So now I have to put in more energy to create the same temperature difference.
Oh,
It's like
same
trying to heat up
temperature
a house with an open window versus one where none of the windows are open. You lose some of your heat. So you're going to have a bigger electric bill to maintain the house at the same temperature. We're losing some of our heat to work here.
Oh, that makes sense.
Good? So whatever this value is, we expect it to be higher than CV. I want you to have that intuition.
How do you calculate that?
We'll calculate it here in a second, but just make sure you got the intuition that this better be bigger than this, so that you don't accidentally get confused on your tables, trying to keep track of which one's which. I want to appeal to your intuition that constant pressure has a bigger one than constant volume.
If you're looking for the same.
For heat capacities, for the same materials. Okay. So now we'll come up with how we relate these two together. Can you erase the picture? Don't really need that. So we're going to start by going back to our good old-fashioned heat equation that we used from before. Heat capacity is equal to, and the one that we were using from before was the number of moles times its molar heat capacity times change in temperature. So this is what we were using in the previous chapter for heat. The differential form of this is if we add a very small amount of heat, then that's going to be the number of moles times CV times a very small change in temperature. Right?
Yeah.
How's the best way to say this? During this process, so when we're heating up a gas in a constant volume, none of the heat can go into doing any work. So all of the heat had to go into internal energy.
Can you say that again?
So when we're talking about constant volume, so try and just draw a picture over here. So over here we're in CV world. Remind us that we're in CV world over here. Constant volume.
Mm-hmm.
Okay, so I know that dq is equal to ncv times delta t, or sorry, that's q. And so dq is equal to NCV delta T, right?
Okay.
I also know, in every world, but also in CV world, that du is equal to dq plus or minus dw.
Yes.
But what is the work done by a gas if the volume stays constant?
0.
0. So du is dq,
For CV.
because this is 0. Yes, in constant volume world, over here in constant volume world, du is equal to dq, and it's also equal to ncv dt.
Gotcha.
So, if this much heat goes into heating up a gas, then the internal energy changes by this much. Probably restated something obvious there. Okay, so now come over here where we're just in constant pressure land. So now volume can change. So du now is still equal to dq minus dw, right?
Yeah.
Over in constant pressure land. dq now is going to be equal to so our only difference is we're going to be switching this from a V to a P in constant pressure land, right?
So the formula still applies?
Yes, this formula still applies. Q is equal to N times its molar heat capacity times its change in temperature.
Okay.
You with me on that?
Why is it the same?
Same formula, different constant.
Oh, so the constant varies.
The constant changes.
Okay.
Constant for constant volume is different than the constant for constant pressure. Sorry. Let me say that different. The heat capacity for constant volume is smaller than the heat capacity for constant pressure.
Yeah, and we showed that.
Okay. So now, when we have this equation, I now know that dq is equal to n cp dt, right?
Mm-hmm.
dw, what's dw when we have constant pressure?
dW when we have constant pressure? Just pressure times your change in volume.
Pressure times your change in volume.
Okay.
Good?
Yeah.
And now, for a given temperature change, our internal energy changes by the same amount. So over here, we still have NCV dt. For a given temperature change, remember that the internal energy of your system only depends on the temperature. That's true for an ideal gas. Temperature and internal energy are talking about the same thing. If internal energy goes up, temperature goes up, and vice versa.
Yes, that makes sense.
So internal energy only depends on the temperature. So if you create the same temperature difference, if your dT is the same here as it is here, then your du's have to be the same.
Yes.
No matter what the pressure and volume are, if I increase the temperature of my gas by 1 degree Celsius, the internal energy of that gas changes by the same amount. The internal energy of a gas depends only on its temperature. Let me read the author's verbiage one more time.
Yeah.
The internal energy of an ideal gas depends only on its temperature, not on its pressure or volume. So if we get the same change in temperature here that we get over here, same dT, then our change in U has to be the same in both. So over here we're in constant volume world. We raise by temperature dT.
Mm-hmm.
Here's the math. Over here we're in constant pressure world. We raise by same temperature change dT. Here's the math. So du has to be the same in both scenarios.
Oh, I see.
That's the crux. And once you get that, I think you're pretty good from here. You think you got that?
Yeah.
Still weird?
Maybe I just need a little bit.
Yeah, feel free to look at it for a second. let me write the equation. This equation over here is this. So this is our du is equal to dq plus dw.
We wrote a C instead of an N.
Or minus. I wrote,
N.
thank you. I don't know. Is that helping? In both cases, we increase the temperature by the same amount. So the internal energy, the kinetic energy that our gases are bouncing around with are the same then. If they're the same temperature, their kinetic energies are the same.
Okay.
du, in this case, is just talking about kinetic energy. So whatever the kinetic energy is over here, that gas has to have the same kinetic energy over here. The internal energy of the gas has to be the same. Over here, we had no work. Over here, we had some work.
Okay.
And so this quantity, the heat added over here, has to be bigger than the heat added over here.
That quantity is bigger. Oh.
This is bigger than this, because this minus some work gives me this.
Yeah.
Good now?
Mm-hmm.
Okay, so over here we're in constant pressure land, right?
Mm-hmm.
So over in constant pressure land, let's, well, we're still talking about an ideal gas, so let's write that. PV is equal to N, well, first we'll just write this equation out, then we'll make sense of this. So PV equals nRT, this is always and forever true, right?
Yep.
Now, if volume is allowed to vary and temperature, if my temperature now varies some amount dt, N's a constant, R's a constant, if we get some infinitesimal dt change in temperature here, then over here, if pressure is constant, then the only thing I can change is our volume. So, in constant pressure world, if we get a small change in temperature, that results in a small change in volume for an ideal gas.
Okay, I see where
You
you're
with me?
Mm-hmm.
So PdV then is equal to nR dt. So this over here can be rewritten as nCp dt minus nR dt. And that's still equal to nCv dt. You with me? That
Okay.
substitution okay? Alright. Now we can cancel out n's on both sides. And we can cancel out dt's on both sides. And so we get Cv is equal to Cp minus R, or Cp is equal to Cv plus R. And that's true no matter what Cv is. So Cp is always equal to Cv plus R.
So you're very.
In the case where Cv was 3/2 R, Cp was 5/2 R. In the case where Cv was 5/2 R, Cp is 7/2 R. Cp is always one more R than Cv.
Okay.
And that's the relationship between the two of them. That make sense?
Yeah, that makes sense. Yeah.
Okay, so those are your different heat capacities. Now remember that when we were calculating Cv, I stressed it over and over and over again that we were way oversimplifying for Cv, right?
Mm-hmm.
Way.
Way
Yes.
oversimplifying.
Yeah, we went over that.
Yes. And so Cp depends on Cv, and so it's also depending on oversimplifications. And so there's a table of a bunch of these different quantities listed out. They're not going to come out exactly like this. They're just going to be close.
For CPs?
For Cps and Cvs.
Gotcha.
Because Cp depends on Cv. And Cv, we did some gross approximations to come up with those numbers.
Yeah.
Good? Okay, so now we finally have one more quantity to talk about, one that we had to use forever ago, and we got stuck forever trying to figure out what it was for helium. And that's our gamma now. So gamma, new constant in this chapter, and it's defined to be Cp over Cv.
Your change in. Isn't that just R?
No, not necessarily. It's definitely not R, actually. R's cancel out. Because, let's think about it now for helium, the problem that we got stuck on forever because we didn't know gamma for helium and had to look it up.
Yeah.
Helium is a monatomic gas. So for helium, our gamma for helium is equal to, for a monatomic gas, CV is 3/2 R, and CP is CV plus R, so it's 5/2 R. Right?
Mm-hmm.
The R's cancel out, the 2's cancel out, and you're left with 5/3, which is 1.4, which is the number we went and looked up. No, I did something wrong. What did I do wrong? I don't know. Something obvious.
That's not how you do.
Am I misremembering? Five thirds is 1.6. 66666. How did I get 1.4? Can't believe you guys didn't let me write that. 1 2/3. So 1.67. Okay. Which is the gamma for helium?
Okay. Yeah, no, we did search that.
And we did search, and that was the value we ended up finding and plugging in to that other formula. So for some reason unknown to man, the author gave us that gamma way earlier, and we had to use it. So that gamma from our previous sections, when you had a gamma in your formula,
Mm-hmm.
when we were talking about, I think it was for calculating speeds of waves in gases, and there was a gamma in that formula. This is the gamma in that formula.
You mean that one that we got stuck on forever?
Yeah, we got stuck on one forever simply because we couldn't find the gamma for helium.
Yeah, that's right.
On one of your homework problems, I think it was.
Sound waves in a gas.
Sound waves in a gas, yeah.
Velocity.
So, that's where that comes from. Alright, let's do a quick example with this stuff and then move on. A typical dorm room or bedroom contains about 2,500 moles of gas. So for our example problem here, we're doing N is equal to 2,500. Right? Little n counts our moles of gas.
Yeah.
Big N counts our actual molecules. Find the change in internal energy of this much air when it is cold from 35 to 26 degrees Celsius. So our temperature, T1, is 35 degrees Celsius. Our temperature, T2, was it 26 degrees Celsius?
I don't remember.
And 26. Obviously, the pressure in our room, both before and after, so I'll just say P instead of P1, P2, is 1 atmosphere, which is, do we remember how many pascals?
1.013 times 10 to the 5.
1.3 times 10 to the 5? I think there's a 5 over here. Jump ahead in his work, see if I can find it. Well, I don't see where he converts it, so we'll come back to that as needed. And then for air, our gamma is, for air, it's going to be 5/2 over 3, or 7/2 over 5, so 1.4, I think. Air, because air is made up of a bunch of diatomic gases.
Yeah, that makes sense.
Oxygen gas, nitrogen gas, but then you have carbon dioxide. Treat air as an ideal gas with gamma 1.4. Okay, so that anyways, but why air 1.4? I guess most of it's going to be diatomic gases. And diatomic gases, for diatomic gas, your CP is 5/2, or sorry, your CV is 5/2 R. And so your CP is 7/2 R. And so that comes out to 7/5, which is 1.4. So that's where that number's coming from. Okay, so we have our numbers, and we were looking for the change in energy, the heat.
Your DU.
Find the change in internal energy. So we're looking for delta U. So delta U, in our case, is going to be, it's in our room, so we're assuming a constant volume.
Constant volume.
Yes. We're assuming that our room, the amount of air in our room isn't changing.
If it's constant volume, then there's no work.
Right, so there's no work, so du, then, our change in U is just going to be Q, which is going to be N times CV times our change in temperature, delta T.
And how do you find CV? Do you know CP? I guess you can find CP. And once
I
you
know
CP,
that.
you can find CV.
CP over CV is equal to 1.4.
Isn't CV just 5/2 R?
Isn't CV just 5/2 R?
Yeah,
Yes.
it's just,
Okay, so you know CV.
Yes.
Just plug in your.
But we could have solved for it, and I want to make sure you know how to solve for it rather than just seeing from stuff I already wrote up here. For any gamma, you should be able to solve for it.
How would
So
you-
this was gamma over here, 1.4, right? I want to make sure you know how to solve for it. So how would I have solved for CV in this equation? Replace CP. CP is the same thing as CV plus R. Over CV is equal to 1.4.
R is. Oh, I see.
And now you have one variable, one unknown, because R is a constant. And then you can solve for CV. And yes, you would have found that CV, in this case, is equal to 5/2 R. But I want to make sure you know how to solve. So remember that you need to substitute this in with CV plus R. And then I assume you know how to solve from there. Multiply both sides by CV, get all your CVs on one side,
Yeah.
and your R on the other. Okay. Alright, so that will be our CV, that's our N, and we know our delta T. Our delta T, remember, is a negative number. We're going from 35 to 26, so we're going down 9 degrees. Right?
Mm-hmm.
So we have 2,500, that's our number of moles, times 5/2 R. Oops. Times R. Times our change in temperature, which is -9. And so negative 468 times 10 to the 3. Or times 10 to 4. No, times 10 to 3, sorry. Joules. Why am I writing that way? Come on, let's try it this way. To 5. And let's see his answer. Negative 4.68 times 10 to 5 joules. Okay, same thing.
So why is your change in U negative?
Because the temperature went down.
Oh.
So the internal energy of our system went down. In this case, you can pretty much just think about it as the kinetic energy of the gas. The kinetic energy of the gas, it went down. By how much? That many joules.
Okay, that makes sense.
So for most cases that we're talking about, the internal energy is just the kinetic energy of the gas. How much it's jiggling around.
Okay.
Okay. So now we have a bit to say about adiabatic gases, and then we're done. And calculating the work done by an adiabatic gas.
Adiabatic.
What's that?
It's just what you said.
Adiabatic. So that's the last one that we haven't calculated work for, right?
Mm-hmm.
Well, we calculated that delta U is just equal to negative work.
Right, but now how do we calculate the work?
Gotcha.
So, well, first off, always and forever, what's our equation for calculating work? Work is equal to the integral from V1 to V2 of our pressure times dV, right?
Mm-hmm.
And with an adiabatic process, like you already said, the adiabatic case, Q is equal to 0, and so our internal energy, delta U, is also equal to negative our change in work. Negative our work, right? Or written as an infinitesimal, du is equal to negative dw.
Okay.
Or dw plus du is equal to 0. Good so far?
Mm-hmm.
All right, let's see what substitutions we like. So we could have it written this way, but I guess the way that we're going to come at this is for an infinitesimal amount of work, dW is always equal to pressure times an infinitesimal change in volume.
Mm-hmm.
Work is equal to the integral of all our infinitesimal works,
Mm-hmm.
which is equal to the integral of pressure times dV.
Okay,
Same
I
thing.
see it now. Yep.
Okay. So we're just not going to go straight to calculating this. I guess we're going to do this in concert, all together in one go. So substituting in dW here for pdV, and let me keep the order the author has the same. Oh, he does a lot all in one go. All right, we'll just play with it and see where we get stuck. All right, so dW then is the same thing as pdV plus du in du, which is going to be ncv dt, right?
This is where your volume is constant though, right?
No, nothing's assumed to be constant.
CV.
Oh, CV is a constant, but I mean between pressure, volume, and temperature, nothing is assumed to be constant. Your temperature could change, your pressure could change, your volume could change.
Don't you only use CV when your volume's constant?
Yeah, I'm confused with that as well.
No. I shouldn't have erased what we had right here. Remember what we had over here when we were using CP. So one of the equations I just erased, let's come right over here. So if P is a const, then we had this worldview. We still had du is equal to dq minus dw. Or we had nc sub v dt is equal to nc sub p dt minus
pdV.
pdv. Notice
Now I see.
pressure was constant, that's this. That was for heat that went into the system. But once we calculate how much heat it takes to raise the temperature of a gas, some amount, that energy is always the same. It doesn't matter that we did that with constant volume.
Okay. Yeah, I see it now.
It's just that when the pressure was held constant, some of the energy also went to work. So the amount of energy that goes into heating up a gas, or that goes into its internal energy, is this much. Even though volume is changing.
And that's only when pressure is constant.
Well, this was when pressure is constant, But this is the the change in the internal energy every time for an ideal gas. Because the change in the internal energy depends only upon the change of temperature. It doesn't matter if the pressure is constant or changing. It doesn't matter if the volume is constant or changing. The internal energy depends only upon the temperature. So find how the internal energy is changing in a case that's easy, like where the volume is constant.
But you said it takes more heat.
It takes more heat to get the same temperature change. Because here's the heat. Some of the heat goes to this. But this much heat still goes to changing the internal energy. If you get this much change in temperature in the internal energy, you have to use this much energy. If you get this much change in temperature, you always have to change the internal energy by this much. The internal energy only depends upon a change in temperature. We found it in a particular case, so for all our ideal gases, du is always going to be equal to NCV dt. This is the amount. If you have that temperature change, you have this internal energy change. The change in the internal energy depends only on the temperature.
Yeah, only on the temperature. Okay.
But you said the pressure changes how much is required to do the temperature.
The pressure changes how much energy you need to get the same temperature change. But if you get this much temperature change, then you got this much energy change.
But you use more energy.
However much energy you get to change the temperature is how much energy you get to change the temperature. And that could be changing volumes and other things. But the internal energy, if the temperature changes by this much, the internal energy has to change by this much. No way around it.
What if there's less pressure?
That doesn't change the kinetic energy of the atoms vibrating around. Well, pressure could affect the temperature.
Yeah.
So if I increase the pressure, who cares that I increase the pressure? As far as the internal energy cares about, all it cares about is, did that change the temperature? And increasing the pressure can change the temperature. And decreasing the pressure can lower the temperature.
Didn't you say it takes less energy to get the temperature when it's higher pressure, when it's high pressure versus low pressure?
So, thinking about back to over here. This is what you're talking about, right?
Yeah.
The amount of energy that goes in right here, well here, this is energy leaving the system. It's cooling down. The temperature gets lower, our pressure stays the same. So right here we have energy flowing out of the system, which means right here we have energy flowing into the system.
Mm-hmm.
Okay, so this amount of whatever energy flows out of the system in lowering the temperature from that volume to that volume, keeping the pressure changed, that energy flowing out, leaving, is less than the energy flowing in right here.
Even though the temperature changes the exact same.
Even though the temperature changes the exact same. Let me think about that for a second. Yeah, that is weird. Oh, because I'm being super dumb. Let's go back and talk about this picture really quick, this clarification, and then move on. So, back to this picture. I gave you bad intuition for that. That's not where the energy is coming in and coming out. Because we have energy flowing in right here as well.
On which line?
When it's going from here to here. So let's think about what's physically happening here. We're talking about we've got some gas. Here's a piston. We've got some gas here. And we're saying that the volume increases, but the temperature stays the same. Right? That's going from here to here. The only way for the volume to increase up to here, with the temperature staying the same, so normally, if we don't add any heat to the system, and I just increase the volume to here, the temperature of the gas goes down, because gas does work.
Okay.
Yeah.
So if I keep the temperature the same, it had to be on a hot plate, putting energy into the system. And so we have to be adding heat right here.
Adding the Q.
Adding the Q. So Q is coming in right here, during that part of the process.
Okay.
So in the net, energy's added. Heat's added, I mean. As we go through a full cycle, more heat is added than heat is removed. Because work is done by cycle.
So is the Q going from V2 to V1, and then from T1 to T2 the same?
We could calculate each of these. We just have to break it up to all these different cases. Because from here to here, we have an isothermal case. From here to here, we have an isobaric case. And from here to here, we have an isochoric case.
Mm-hmm.
And so we can calculate the Q and W for each of those and see what they all are. Because we now know how to do that, right?
And are they the same?
Well, right here, the work and the heat added are the same. Because the internal energy is the same. So whatever the work is for this part, the heat is the same for that part. Here, we're losing heat. And here, we're gaining heat.
Is that heat the same?
Well, here, actually, we're not gaining heat. I should say that. Here, we're just decreasing the volume. So this could be flat out temperature increase from compressing it. So this could be nothing to do with heat.
But your temperature's going from T2 to T1.
Right, but that could be just from me compressing it.
Doesn't compressing heat it up?
It increases the temperature. There could be no heat source up.
But you're letting it leak out the heat.
So from here to here, no, temperature is going up, volume's going down. I'm not sure what I said before, so I might be confusing you from before. So let's say it right now. The volume's at V2, it goes to V1. So this is me pushing down on the piston myself.
Mm-hmm.
And I'm pushing down on a piston such that I maintain the pressure a constant. I'm not sure if I would have to also add heat or remove heat from the system at the same time to make that work.
You would have to be removing it.
But I'm definitely doing work on the system. I do this work on the system, the area under this curve.
Isn't that accounted for in the Q?
The internal energy drops down. I don't know that any heat has to be added to the system.
It has to be taken out.
I don't think heat is added or removed from the system. I think it might just be the case that our change in energy in that part, du, is equal to the work done. Negative the work, but I'm also doing negative work, so positive change in energy. Since it's me doing the work, the system's not doing work.
Where does the heat go?
Well, that's what I'm saying. I'm not sure that there has to be any heat for this. Because delta U equal to Q minus W. We know that delta U goes up because the temperature went from T1 to T2.
Doesn't that mean it goes
Oh,
up?
the temperature went down. Sorry. Yes, temperature went down. This is work done by the system.
Mm-hmm.
This is work done by the system. So if I do work, then that's a negative number. The internal energy should go up. So you're right, heat has to be flowing out of this. So Q has to be flowing out. Because Q has to be equal to delta U, the negative of delta U, plus the work. And that's going to be a negative value.
Why isn't it positive U plus work?
Oh, thank you. Our U is just negative.
Yeah.
So the temperature went down, so our delta U is negative. So Q, let's just write it all the way out if we want. Q, in this case, is equal to NCV delta T, whatever our change in temperature is, minus P V2 minus P V1, or PdV if we delta V. That's how much heat had to, that's our heat. Where our delta T is also negative. Sorry, I'm being equivocal. Let's just keep everything exactly how it should be. V1 minus V2, that's going to be a negative number. And NCV is going to be T1 minus T2. Okay, so that's going to be a negative, that's going to be a negative. So heat definitely has to leave the system during this part. And that's how much heat.
Is that the same amount of heat as is entering the system when the volume is staying the same with the temperature?
You're saying right here?
Yeah.
So the heat there, Q in that case, is just equal to, in that case it's just going to be NCV T2 minus T1. So that only cancels out that portion.
Then what are you doing to it?
Well, this is canceling out the work down here. This portion is the work here. When we did this, we did the work for everything under this curve. This cancels out that portion, leaving this much work left.
Yeah, but you're saying you do that much work to get rid of the temperature, and then you do less heat to get the same temperature.
The heat that flowed out right here had to account for the work, this work right here, this portion of the work, and the same amount of heat that we raised right here.
Where is that same amount of heat?
This is the heat going from here to here. This is the heat going from here to here if we ignore the heat that goes into canceling out that work. And those are the same, just opposite. So those cancel out. Here's the heat from canceling out this work. And then we have the work that we do here, which is all of this, which means the heat that's added here is just this portion of heat. And then everything's accounted for. I don't know. Let's continue with the material. If you're still confused about that, we'll break it down and we'll put numbers in and we'll solve this completely out. Okay, so back what we were talking about, this adiabatic process. Adiabatic process, we have the work plus the internal energy is going to be a constant. There's going to be zero since there's no heat added. That's what we mean by adiabatic process, right?
Okay.
Replace our work, P dV and du, NCV dt. U only depends on temperature. It's a function purely of temperature, nothing else.
Okay.
So a small change in U depends only upon a small change in temperature, nothing else.
Yeah.
Changes in pressures and volumes might also change the temperature, but it's the fact that they change the temperature that changes the internal energy.
Mm-hmm.
Okay. And then P dV over here, where can I write that? We've already made the substitution once. Well, let's say we have PV for our ideal gas. PV is equal to nRT, right?
Okay, and then you.
And so solve for P. P is equal to nRT over V.
So you plug P in.
So I'm going to make that substitution for P here.
Okay.
So making that substitution for P, we have nRT dV over V plus NCV dt is equal equal to 0.
I'm with you.
Okay? I'm going to divide both sides, divide through by nRT. Divide everything by nRT.
And
nRT.
well, you're going to end up with an R on.
That's fine.
Okay.
So when we divide this, we get dV over V. Plus, when we divide this by nRT, the n's are going to cancel out, and we're left with CV over R times dt over T is equal to 0.
Well, what is dV over V?
Well, we can integrate that. So now we're going to integrate this from point 1 to point 2.
And the point 1 and point 2 has a volume 1 and
V1,
temperature.
T1,
Okay.
and to V2, T2.
That's
Whatever those points are, we know nothing about. So then we're going to integrate this from point 1 to point 2. That's point 1 to point 2, not number 1, number 2. And we're going to integrate this, we can bring the constants out, from point 1 to point 2, same thing. Right?
That is CV.
Yes, thank you. Good catch.
Okay.
Okay? And so from point 1 to point 2 over here, what's the integral of V? Or what's the integral of 1 over V?
Isn't that natural log?
Natural log. So over here we're going to get natural log, we're going to get natural log of V2 minus natural log of V1, or V2 over V1, same thing, right?
Okay.
Plus, over here, we're going to get CV over R times the natural log of temperature at 2 minus the temperature at 1 is equal to 0.
Okay.
Good?
Yeah.
Okay, remember this rule from exponents. If I have a times the natural log, why do I keep doing that? Times the natural log of b, that's equal to the natural log of b to the a. You can bring the exponents out front.
Yeah.
Natural log B to the A.
Mm-hmm.
So T2 over T1.
So I'm going to put this as an exponent there. So then we get natural log of v2 over v1 plus natural log of t2 over t1 to the c sub b over r is equal to 0.
Why are you doing that?
Because now I can combine the logs together. A sum of logs is their product. So now this is the log of v2 over v1 times t2 over t1 to the power of cv c sub b over r is equal to 0. You with me so far?
Yeah, I'm with you.
All right. So now, if a natural log of something is equal to 0, then what does the inside thing have to be equal to?
Is it 1?
Did I make a mistake somewhere? Oh, right. You're right. So e to the power of 0 has to equal this whole thing. But e to the power of 0 is always 1, so everything inside the log has to equal 1. So we get v2 over v1 times t2 over t1, this one to the cv over r is equal to 1. And we can flip that over to the reciprocal. Let's see what they end up getting after here. Okay, so they just put the denominators over there. So I'm going to multiply both sides by v1 t1 to that. And so v2 t2 to the cv over r is equal to v1 times t1 to the cv over r.
Oh, so they're directly correlated with each other?
Mm-hmm. V1 times T1 to that power is a constant, is another thing that this tells us. So rewriting the exact same information, this is telling us that V times T to the CV over R is a constant. Same thing.
Oh, I see. So once you know one of each and then the other one, you can just solve for the other?
Yeah, so they're always related this way in an adiabatic process.
Okay.
Now, get rid of that way of writing it for a second. Sometimes we want the volume to be to an exponent rather than the temperature. So I'm going to raise both of these to the power of R over CV.
And they cancel out?
And it cancels out on this one and puts an exponent on this one. So we can also write this as V2 to the R over C sub B times T2 is equal to V1 to the R over C sub B times T1. So depending on how you want to move the exponent.
Can you give us intuition for an adiabatic system?
An adiabatic system, that's just one where we're not adding heat. So an example of an adiabatic system is when I just compress a piston really hard. I did work on the system, but no heat was at the system. The temperature will change. The temperature will shoot up.
Yeah.
But no heat was added. We just did work on the system by changing its
How
volume.
about when you let something just sit and cool?
Then heat is slowly leaving.
Oh.
And that's
Yeah.
no longer an adiabatic process. So an adiabatic process needs to be, in the real world, they need to be kind of sudden processes. So it doesn't have time to just sit there and cool.
Okay.
Relative to what's going on, no heat transfer can really happen.
Weren't we looking for how to solve for work?
Oh yeah, we're not done yet.
Oh, okay.
No, these are useful relationships that are good to have.
Is this how we solve for work?
Yes, we're going to use this to solve our work.
Okay.
Because, erase over here. Maybe jump ahead to where we're going and then go back to giving you useful stuff. So our work for an adiabatic process we have right here.
Yes, but how do you solve for that work?
Right.
Oh, I see.
So the work on the system is equal to U NCV times our change in temperature. Sorry, negative work times our change in temperature, T2 minus T1. Negative work is equal to our change in internal energy.
Your change. Oh, because you're I see it.
That's right there. Change the order that we write the temperatures in, eats up a negative sign. So I'm going to flip the orders there to eat up that negative sign. So it's work is equal to NCV times T1 minus T2. Okay, now how do we get T1, T2? That's going to be from these relationships.
I see.
So if you only have the volume, you can use the volumes now to calculate your temperatures. And let's also get this with the pressures plugged in there. What's the best way to see this for pressures? We'll just plug it in and see how everything cancels. Okay, so here's one way you can get it. Now, T1 and T2, we can solve for those because we know from our ideal gas equation, from our equation right here, if we solve for T, let's write that up here somewhere where we can see it. Those correlate with that, you might care about that. We'll just write it down here. Right down here. So from our ideal gas equation, if we solve our ideal gas equation for T, we get T is equal to PV over NR, right?
Mm-hmm.
So now I'm going to make this substitution into this equation
For your T?
for my T. So I'm going to replace T1 in terms of P1 and V1, and T2 in terms of P2 and T2.
Will you just plug it in and I'll see
Yeah.
it?
Okay. So now we can also say work is equal to, probably need some space, work is equal to NCV times T1, which is P1 V1 over NR, minus T2 good?
Mm-hmm.
Factor out the NR from both those. The N's cancel out, notice that. N cancels out with N, so we pull out the R. So this is, don't want to go off camera. So we get work is equal to CV over R times P1 V1 minus P2 V2. And there's another way we can get work.
Okay. That makes sense.
Okay, so that's almost our last equation. There's just one substitution into that equation that the author's going to make. So the author gives you, just so that you know, the two equations he gives you for the work are this equation and this equation. So we have it. Now we're just going to write this CV over R slightly differently. Sometimes we like to use a gamma when we're writing that term.
CV over R?
Yeah, in terms of gamma.
So wouldn't that just be your coefficient in front of your R then?
Wouldn't that just be my coefficient over my R?
In front of your R.
Well, we'll just write that real quick. So, starting with R over CV is equal to, let's see the first way I want to write that. Yeah, that's fine.
CV over R or R over CV?
We're going to start with R over CV.
Okay.
It's going to be CP minus CB over CB,
Mm-hmm.
which is equal to CP over CV, that's gamma, minus CV over CV is 1.
So gamma minus 1 is
R over CV, if we want CV over R, that's just a reciprocal of that, that's 1 over gamma minus 1. With me?
yes.
So you'll also see these formulas written. CV over R, I don't think he writes it that way. CV over R, I wonder if I made a mistake somewhere. Shoot, I sure hope not. Coming clear back, where did we get the CV over R? We got it from right here. Which gives us a CV over R. Not a gamma minus 1. R over CV oh, we have it right. I'm just looking at the wrong equation. The author derived this one, not this one.
Oh.
So he has an R over CV, an R over CV. So when he writes out this equation, in the book, when you see this equation, the way the author is going to write it is you have V2 to the gamma, not Y, to the gamma minus 1 times T2 is equal to V1 to the gamma minus 1 times T1. So that's going to be the difference he has. So we just made that substitution.
I see.
Okay. And then in these formulas, when we calculate the work right here, you could have had it written that way, but CV over R, notice that that's the same thing as 1 over gamma minus 1. So another way the author will have this equation written is W is equal to 1 over gamma minus 1 times P1 V1 minus P2 V2.
Isn't that just P1 V1 minus P2 V2 over gamma minus 1?
Yeah, it's just nice to pull it out in front like that.
Okay.
Kind of like how we write kinetic energy as 1/2 mv squared rather than mv squared over 2.
I see.
Okay. And that is the last of it. So that's the end of that chapter. I guess we could do the last example problem if you want. So let's do the last example problem. The compression ratio of a diesel engine is 15:1. That is, air in a cylinder is compressed to 1/15 of its initial volume. If the initial pressure is 1.01 times 10 to the 5 pascals and the initial temperature is whatever. All right, let's start getting some numbers up here for this last one. So we've got some diesel engine and it's going to compress a piston really fast.
Oh, is this our car?
We'll have a lot more to say about cars in the last section, but so a diesel engine has a piston, compresses a gas in a cylinder really fast. So the initial volume is V1, whatever the final volume is V2, it's 1/15 V1.
Oh, okay.
And then he gives us our pressure at time 1 is equal to can't find it. 1.01 and 27 degrees Celsius. 1.01 times 10 to the 5. And our initial temperature is equal to 27 degrees Celsius. Is that what I said?
Yes.
Okay. And then, find the final pressure and temperature after the adiabatic compression. How much work does a gas do during the compression if its initial volume is whatever? Okay, so let's see. If the initial pressure is this and the initial temperature is this, find the final pressure and the final temperature. Okay, so final pressure and the final temperature when we undergo an adiabatic process. So here's how we're going to get our final temperature. So I know T2 is equal to V1 over T1, or V1 over V2 to the gamma minus 1 times T1.
Yes.
Right? Now, the gotcha here is these temperatures always need to be in Kelvin.
Oh, so we're just going to have to move it.
So T1 is really not 27 degrees Celsius, but what is that in Kelvin?
It's like 300.15.
Yeah, 300.15, right? Kelvin. And then this will give us T2. And I assume it gives us the gamma for our gas, or for the air in there, which is 1.4. So I know a gamma is 1.4. So now we can find our second temperature.
Yes.
V1 over V2 is equal to 15. 15 to the 0.4 times T1 gives us our final temperature. So 15 to the power of 0.4 times 300.15. So that gives us our final temperature in Kelvin. And now I need a minus 273.15 if we want to get back in Celsius. and we get roughly 614 degrees Celsius,
That's all.
and he has 613 when he rounds it, so he has a round here. T2, 614 degrees Celsius
Okay.
is our final temperature. And final pressure. Okay, I don't know if I made those substitutions in there. We didn't take this equation and plug in pressures, did we?
Well, how would you plug in pressures?
Same way we plug in temperatures from before. So, let's try that one out real quick. So, we'll write how the author has it. Just up here. So we start out with, we have our T1, V1 to the gamma. Well, let's just do T over V to the gamma, and then we'll go back to that. To the gamma minus 1 is equal to some sort of constant. That's this equation right here. This one, right? Just different order.
Okay.
Okay, so now we substitute in our temperature from our ideal gas equation. Ideal gas, we know that PV is equal to nRT. Solve for T, plug in.
Oh, I see.
And so we get PV times V to the gamma minus 1 over nR is equal to a constant. You with me?
Mm-hmm.
N is a constant, R is a constant. So
Okay, just
multiply both
another
sides,
number.
just gives me another constant,
Yeah.
whatever it is. V times V to the gamma minus 1, that's going to be P times just V to the gamma is equal to a constant.
How does that work?
V is V to the 1. V to the 1 times V to the gamma minus 1 is V to the gamma.
Okay.
Your P's here, multiply those to the other side, constant times a constant, just some other constant.
Okay, I see it.
So, since that is a constant, then I also know that P1, V1 to the gamma is equal to P2 times V2 to the gamma. And that's our pressure equation. Okay, so back over here, we do almost the exact same thing now. Now I can find my pressure at time 2. That's going to be equal to, we had it with volume. It's going to be my volume at 1 over my volume at 2 to the gamma times my pressure at 1, right? And so now in this case, we take 15, we raise that to the power of 1.4, and we multiply that by our initial pressure, which was 1.01 times 10 to the 5. And it comes out to 4.48 times 10 to 6. It comes out to 4.48 times 10 to 6 pascals. And double check that with what they got. .48. Oh, 44.8 times 10 to the 5. And we did 4.48 times 10 to 6.
Yeah.
Okay, so that's how you calculate that. And then they said, then calculate the work done in this process. Okay, how do we calculate the work? The work, we can use this now.
Oh, you could use. Oh, never mind. Yeah.
So our work is 1 divided by 0.4 for this term, right?
Mm-hmm.
Times our pressure. Oh, we don't know our volume, do we? We don't know V2. We just know it's 15 times V1. So,
Doesn't it give us V1?
so it might be easier to use just CV, and then T1 minus T2, the temperature. Let's see which one they use. P1 V1 times P2 V2.
If I'm not mistaken, I thought.
Alright, let's just do the algebra with this and then plug in.
Okay.
So, how are they going to get the volumes to cancel? From equation 19.6, the 19.26, the work done is equal to that, okay? Using V1 over V2 equals 15, this becomes pressure how do you know what V1 is though? Oh, I didn't read all part B. Part B says how much work is done if the initial volume is it gives you the initial volume. Okay. So, should finish reading the problem before we try to solve everything. Okay, so how much work does the gas do during compression if the initial volume of the cylinder is 1 liter? So V1 is 1 liter, which is 1,000th of a cubic meter. So V1 is 0.001 meters cubed.
Okay.
Okay. And then now we know our final volume because it's obviously 1/15th of that, right?
Yeah.
Okay, so now we can do all of this. So we have 1 divided by 0.4 times P1, which is 1.01 times 10 to the 5, times V1, which is 0.001, minus P2. P2 is
4.
that big number, so go find it, plug that in, times V2, which is V1 divided by 15. Okay, and then 494 joules. Negative 494. Negative 494 joules. Okay.
Why is it negative?
Because it's compressed. So the work done by the gas is negative. We did positive work on it.
Gotcha.
And there's the answer. Okay, so now we got everything.
Okay.
All right, so that's the end of that. That's the end of 19. That's the end of chapter 19. 1 chapter to go.